Hello and welcome to Eng Phys 3BA3 Lecture 14, D to A and A to D Converters, Analog versus Digital Information. If you want to send somebody the number 3.74556 through an electronic signal, you can either just send them the number, like send them a voltage level and let them understand how to interpret that as this number, like maybe you send them exactly 3.74556 volts, or you can encode the number into binary and then send that, maybe by a sequence of pulses at predetermined times. Now, since binary is either 1 or 0, the accuracy of any individual voltage measurement doesn't have to be nearly as good for binary, and it's much less lossy than sending analog information is. Unfortunately, when you initially convert to and from binary, that's when some of the losses can sneak in. And if you do end up dropping a bit in binary, then it's usually a much bigger error than if you were to drop like a certain percent of the signal in analog. That said, dropping a bit in binary is very rare. So storing information in storing bits in circuits is done mostly with registers, and registers are made up of flip-flops. Flip-flops are also known as bistable multivibrators. If you look at the course description, the course outline, it says that we go to one of the main things we learn about are multivibrators. You may look through the course notes and say, well, what the heck is a multivibrator? Did we even learn about that? Yes, we did. Multivibrators are flip-flops, and we talked about those a lot. So that's it's one of the important things that we're going over this course. Okay, now D to A and A to D conversion. First, let's talk about D to A conversion. How do you convert a digital signal to analog? The easiest way is just add up the voltages and output them using an op-amp. This is a summing amplifier. So we've got the signal V0 is the least significant bit, and then more significant, more significant, more significant. You can see that because of the resistors here, we end up multiplying V1 by 2 times whatever we multiply V0 by, V2 by 4 times it, and V3 by 8 times it. So that means that we end up with a signal which is proportional to the input number, and then we can amplify that up by choosing what our F is. So it's an output signal that's proportional to the V0, V1, V2, V3 implemented as binary. So all the V0s through V3s are either maybe, let's say, 0 or 5 volts for logical 0 or 1, and then the output will be proportional to the binary number of those voltages. Okay, analog to digital conversion is a bit more involved. So how do we take an analog signal and convert it into digital initially? Well, one way is using this. So we've got 2 different steps. We've got a bunch of comparators, and here we're just showing the output of the comparators, and then we've got some encoders. So this whole thing collectively is called an encoder. The encoder takes the output from the comparators and turns it into a binary number. So here we've got the least significant bit, a little bit more significant, and the most significant bit. This is a 3-bit encoder that we're showing here. You can imagine that an 8-bit encoder would be quite large indeed. So here's how this works. The comparators on the left are saying, is the analog signal bigger than V over 8? Bigger than the target voltage over 8, let's suppose, or the voltage range over 8? If it is, then this is a 1. Is it bigger than V over 4? Then this signal's a 1. Is it bigger than 3V over 8? Then this is a 1. Is it bigger than V over 2? 5V over 8? 3V over 4? 7V over 8? So we've got 8 different intervals that we're talking about. If it's less than 1/8 of the range, then all of these are 0. If it's more than 7/8 of the range, then all of these are 1. So what should we output in those situations? If it's more than if it's all 0, then we should output 0, yeah? So let's check that works. So every input is a 0, and we've got zeros to exclusive OR, so that's a 0, and then zeros here, that's a 0, zeros there, that's a 0. Where does this one go? This goes right into that OR gate. Okay, so all of the inputs to all of the gates are just 0, and so we get 0, 0, 0. That worked. Now let's pick another voltage level. What if it's bigger than 1/8? But that's all it's bigger than. So as soon as it's bigger than 1/8 of the total swing voltage, we expect the output to be a 1 for the least significant, then 0 for those. So 0, 0, 1 would be our first encoded bit. And since all these other ones are 0, the rest of that's going to work out the same. But this is now outputting a 1, so we get a 1 there. What about if it's bigger than 2/8 or V over 4? Then we've got this is a 1, and this is a 1, and so now the exclusive OR outputs a 0. And what else do we get? Well, this exclusive OR now outputs a 1, and so this OR outputs a 1, and we get 0, 1, 0 for the next bit. As the voltage level increases up and up and up, then you can see it's eventually going to go all the way to 1, 1, 1 when we're above 7 V over 8. Let's see if that works. So above 7 V over 8, then all of these are a 1. So this is a 1, all right? And let's trace the other ones. This is these are both a 1, so all the exclusive ORs are outputting 0 now, but that's okay. They out because we've got the 1 from this top bit into the 4-input OR gate, and this is outputting a 0. But we're above 3/4 of V, so we get a 1 to this OR, and then the V over 2 output is directly tied to Q3. Okay, so we do get 1, 1, 1 when we're above 7/8 of the voltage range that we're for. So it worked. Now, one problem with this is that it requires a lot of comparators. These comparators each take an op-amp, right? So that's going to be getting quite large as we get as we build a more and more precise digital analog to digital converter, rather. So the A2D conversion this way is very fast. This is called flash A2D conversion. It's very fast. The flash is quite fast, but it's big. It takes up a lot of space. It's expensive. It's not cheap to hire the flash. Okay, so what can we do instead of that? Well, we can do this method, which is a lot slower. This is using a successive approximation register, or SAR. And how this one works is the successive approximation register is outputting a series of numbers. So first it starts off with 1, 0, 0, 0, 0, 0, 0, 0, and then we run this through a D to A, so we convert that output back into a digital circuit. These mean that there's 8 wires going through here, 8 going over to the D to A, and we compare the input to that using this op-amp. So the input doesn't actually go to the SAR, it goes through this one comparator. We only need one op-amp to do it this way. And we say, this is kind of a sequence of higher or lower. It's like playing a game of higher or lower. You know, if somebody asks you, hey, I'm thinking of a number between 0 and 100, and it's an integer, and you get like 6 guesses, and I'm going to tell you with each guess whether it's higher or lower than that number that you guessed. Well, your best strategy is to just split the interval every time, right? So first you say 50, and they go, oh, it's higher than that. And then you go, okay, 75. You want to split the interval. And they go, oh, it's lower than that. And then you go, okay, 62. And then using this strategy, you can zero in on what the actual number is. And that's what the SAR is doing. First, it guesses halfway. And then the comparator says, oh, it's higher than that. So then it guesses 75. And the comparator says it's lower. So it guesses 62.5. Comparator says higher, 68.75. It says lower. Well, really, it's not out of 100. It's out of 10 here. So I guess I should be saying 6.875. It says lower. 6.5625. It says it's higher than that. Okay, so we guess halfway between there and that interval. 6.71875. It says lower. 6.640625. Higher. 6.6796875. It says higher. And now we've got but we don't really do anything with this one because we're as accurate as we're going to get. It says, well, as close as we can get, it's this binary number, which corresponds to this number out of 10. So if we take the total range that we could get from like 0, 0, 0, 0, 0, 0, 0, 0, all the way up to 1, 1, 1, 1, 1, 1, 1, 1, and we take that many digits, we divide. So how many is that? This would give us 4, gives us from 0 to 255, so that's 256 numbers. And another 4 would be 2 to the power of, let's see, 2 to the power of 0, 1, 2, 3. So 2 to the power of 4 for this, 2 to the power of 8 for this. So all in all, I think I said, I'm not sure if I said 256 was just the 4. No, that's wrong. It's 16 is the 4, so 256 is the 8. So all in all, we get 256 different binary numbers representing split between 0 and 10. That means 128, this number here in binary, corresponds to 5 volts, and 11000000 corresponds to 7.5, etc. All right, so how does the SAR actually implement this guessing game? Well, it does it by having a simple set of rules. If the input here, so first off, what it does is it moves 1 bit to the right of where it was thinking, and then it sets that to a 1. All right, so it starts thinking about just off the screen here, and then it moves over to this and says 1. And then it moves to the next bit and says that's a 1. And then it moves to the next bit and says that's a 1. And it moves to the next bit and says that's a 1. Now, as it leaves each bit, it decides whether it's going to leave the bit a 1 as it was set or drop it down to a 0 based on what the comparator is at that time. So first it just sets this to a 1, doesn't look at anything. Now the comparator outputs a 1. So as it moves to the next bit, it leaves the first one a 1. Then the comparator outputs a 0, meaning that it's lower than 7.5. So as it moves to the next bit, it changes that one to a 0. Next bit becomes a 1. Comparator outputs 1. So it leaves that a 1 as it moves to the next bit. Comparator outputs 0, makes that a 0 as it moves to the next bit. Comparator outputs 1, leaves that a 1, moves to the next bit, outputs a 0. So it makes that a 0 as it moves to this bit. Outputs a 1, so it leaves that. Outputs a 1, leaves that. And there we go. So pros and cons. The flash-based method is faster but requires n op-amps. So if we got, if we want 8 possible outputs, it requires 8 possible op-amps to do it this way. The successive approximation register for an 8-bit number requires only 1 op-amp, but takes 8 clock cycles to do it. So it's a trade-off of speed versus space. This one takes up a lot more space, a lot more, especially as n gets large, whereas this one takes up, it doesn't take up any more space. It would just, it would need a slightly bigger successive approximation register, true, but the main problem with this one is time. It takes up another clock cycle per every digit, and if the input is changing quickly, then this is not going to do. You're going to need something more like the flash A2D conversion. All right, design a circuit using standard 2 input logic gates that will have the same property of the 4 input OR gate used in the circuit shown in figure 717. So we've already built up OR gates like this using NAND gates, and we've built up NAND gates using CMOS. So and since you know how to build CMOS from doped semiconductors, you in principle know how to make this kind of gate from sand. And since we're looking at all these complicated structures, we looked at how you can build all these things from that. You've got all the way up from sand to this sort of thing. But how do you make this gate from this gate? Well, that's what this question's addressing. Can you figure it out? All you do is this. You take the input from 2 ORs and then output those to another OR, and then you've got your 4 input OR gate. Exercise 719, design a simple 4-bit successive approximation register using D-flops. The SAR was the critical bit of this A2D converter up here, where the goal of it is to start off at 1000, and then for the 4-bit one anyway, we only need those numbers, and then based on an input bit of 1 or 0 that it generates from the comparator here after D to A-ing its output, it either is going to leave that first bit a 1 permanently or set it to a 0 if this bit was a 0, and then move on to the next bit, set that to a 1 initially, and then adjust it as it moves on to the next bit 1, adjust that one, and then we're done. Okay, so give that a shot. You'll probably need to use 8 D-flops to do this. Okay, here's the answer. At least one of the answers. This one, so I drew this up in Schemat. This is a way that you can make this happen. First, the don't reset is high, and then when you set this to low, you're resetting, and notice that it's wired to the inverting reset of all of these flops, all 7 of these ones, but not this one. This one, it's wired to the set. So initially, they're all going to be 0, except this one's going to be a 1. Now the outputs are taken from the ORs of the top flops and the bottom flops in each kind of column here. So we've got this one and this one going to number 2, this one and this one goes to 3, and this one goes to 4. And by 1, 2, 3, 4, I mean 3, 2, 1, 0. Right, so most significant bit first, then next most, and then the least significant bit. Okay, so initially we've got a 1 output here, and that's going to turn on, set the comparator, and based on whether we're too high or too low, we're going to get our up or down input. So what happens at the bottom? Let's look at this. On the first clock cycle, we transfer a 0 from this over to there, and but before that happens, this was a 1, so we transfer that into this one. So we went 1, 0, 0, 0 to 0, 1, 0, 0. And then the next clock cycle, that's going to propagate down. We're going to go 0, 0, 1, 0. Next clock cycle, 0, 0, 0, 1. Next clock cycle, 0, 0, 0, 0. And then we're done. Okay, so when each of these goes from 1s to 0, they trigger these. And that's the only time that these ones, these get triggered on the high pulse, because there's no inverse here, of this input. And so it's, since it's hooked up to the inverting output of these bottom flops, it's when the bottom flops go from their 1 state to their 0 state. So we get one shot to permanently store in whatever the digit should be. So that means that before that happens, we have to be comparing to the appropriate bit. And sure enough, this starts out with 1, 0, 0, 0. The outputs of this, because the tops are all zeros. And now if it was too high, then we're going to have a 0 there. And so after we switch this one to a 0, and this triggers, we're going to lock in a 0. And now this is 0, and this is 0. So we're outputting just a 0 there. At the same time, we switch this one to a 1. This is still 0. So we're outputting a 1 there. And now if that's still too high, then we're going to, on the next clock cycle, as this one goes down, this gets triggered and locks in a 0. But if it was too low, then we're going to have a 1 here. And so it'll lock in a 1 and keep that 1 there, and so on and so forth. There we have it.